Okay, so let's look at these various different algorithms in the maximum subarray. All right, just gonna do another screen share, and here we are. Okay, so now remember that the divide and conquer algorithm does a handful of things, three things basically. The first is that it looks to the actual um, problem for ways to subdivide it. Once we're able to subdivide, then what we want to do is make sure that we have the simplest subdivision of a problem and then start to combine solutions to find the more optimal ones on the way back, right? So we usually try to work with the simplest of solutions and then try to optimize it over some time by combining the solutions to the sub problems. So if you were talking in the terms of the maximum subarray, then what will happen is as follows. Okay, here you have the max crossing subarray. It takes in an array, takes in the lowest value, the middle value, and the high value. Okay, and that's why we have these arrays right here. So here's how the divide and conquer solution would work. So if we want to find a maximum subarray of the subarray A, low to high, then here's what we would do. We want to divide and conquer by way of dividing the subarray into two subarrays of equal size, if at all possible. So if the array is, remember, if it's odd, we're going to have floors and ceilings because you can't divide something odd into two that easily. So if that's the case, then what we're going to do is to simply divide into a subarray and then try again. But now we find that the midpoint, say mid of the subarray, and consider the subarray A from low to mid, and then the other one from mid plus one to high. So now taking into consideration what we see in illustration 4.4, all right, this is the first half, and here you have mid, and then here's the second half with the mid plus one to high, okay? Now, let's take a look at the terminology that they're using. Here we have the following. Um, in figure 4.4a, right, it shows that any contiguous subarray must lie in exactly one of the following places. First, it's either entirely in the subarray from low to mid, where there's some index between those elements, all right, or indices even, I and j between those elements. And then there's also the possibility that it could be between mid to high, and then to the degree that there would be some I and J that would be between mid and high. Notice that this part here, the I is without the less than or equal to because we're going plus one to make sure that we don't cover the same thing again. Finally, the last case is crossing the midpoint so that we have some I that is between low and mid, and J is between mid and high. Okay, so here they're talking about subarrays going from I to J, right? As opposed to low, mid, or high. So here's what that means. I could have some subarray that is right here, or I could have some subarray that is somewhere over there, or I could have a subarray that is over here entirely, right? So it's either one side, the other, or it spans both sides because it crosses the midpoint. All right. How many people are with me 100% on that explanation? All right, show of hands. And raising your hand is option Y or alt Y. Okay. So now that's one person, two people. Come on, who else? Two people. All right, so let me stop for some questions because I only have three people thus far. Let's hear some questions. All right. Um, so then let me see if I can. Oh, okay, Han, go on ahead. Do you have a question?
Oh
No.
wait, no, I just mean I get it 100%.
Cool. Great. That's what I like to hear. All right. So there are some who are not 100%, right? So now here's the thing. Remember that we don't know when it comes to this group of highs and lows, which high and low have the greatest distance in value. That's why we're using I and J, right? If we take a look at the following, let me just share the book again. We take a look at the following, okay? This whole thing right here, where we saw that the differences were hard to ascertain, what we want to do now is to just take into our consideration all of the different data points. And so for that, we have an array for every discrete data point. So, one or zero, one, all the way to 16. Now, remember that we found that the highest profit would be found if we were at 7 and selling at 11. Okay. So it's not the same as 7 to 8 or 8 to 9 or 9 to 10, 10 to 11. So that's why instead what we have to do are take data points and put them into an array. Now, if this whole thing really did go from 0 to 16, right, that's about 17 different data points. Okay. Here's what that means though. If we want to be able to get 7 to 11, I to J, we notice that we have to pick different samples going across from the array. The way for us to pick different samples is to be prepared for samples of arbitrary size, not just uh, you know, one small interval at a time, but arbitrary size, the way we can find the maximum subarray, the subarray that has the maximum value. So we were starting by measuring changes. For the subarray, however, if if 7 is I and 11 is J, and we have, let's see, 0 to 16, that's 17 different values, right? Cutting that into halves, we would then have the movement from 0 to 8, okay? And then from 9 to 16. So this would be a case in which we actually do cross the boundary between the first half and the second half. How many people are with me on that? By the way, you raise your hand by using option Y or alt Y. How many people are still with me? 100%. Okay, we got Evan gets it. Seba gets it. Um, Nafis gets it. All right. Han gets it. Let's see. Something in the chat. 100% says severe. Great. Let's see. What else do we have? Let me just take a look at what else the participants are saying. Okay, so quite a few people are getting it. Great. Now, as you can see, what we have here is the third case, right? The third case is the one in which our subarray was not entirely in the first half or entirely in the second half. And remember, the reason why we care about this is because we're breaking down subarrays to find out where that particular range was. Now, this isn't as clean as, say, the binary search, where everything broke down and you threw out half versus another half. In this case, we have a solution that could span halves, right? So we got to be careful about that. So now, moving further down, you'll notice that we're not really doing the brute force anymore, the n squared, where we were taking all of those um, subsets of the power set, right? We're not doing that anymore. Instead, what we're doing is as follows. We're now moving to see what the changes were across the arrays. And we see that the maximum subarray went from 7, in which the low was a minus 23 from the time before it. Let's just take a look. Okay, so here's 7, and its value is just above 60. And in the case before it, we had a value that was somewhere close to 85, all right? Now, moving over here, we see that with 10, we've come close to about 95. With 11, we've come up to about almost 110, okay? So that's how we're determining the smaller averages. So taking a look at this illustration, maximum subarray started from 7, ending at 11, okay? And apparently we're not including 7 itself. So it's at the end of the day that the trades are made, if you remember correctly. Here's the maximum subarray. So now, here's how we define what we're looking for. This row of challenges, or I'm sorry, not challenges, row of changes, okay? If we treat them as an array, we then find the non-empty contiguous subarray of those data points, which have the largest sum. So the largest sum of those data points. Here we have going from 7. At the end of the day, we're not going to count the minus 23 because that was a fall from 6. Instead, we're going to say that we rose by 18, and then we rose again by 20. We fell by 7, but that's just 31, a loss, a climb of 31. And then we rose again by 12, so that's 43, right? And that's exactly what we were looking for. If we take a look again, here in the book, they're telling you the following about the sum 43. For example, in the array of figure 4.3, the maximum subarray of A going from 1 to 16 is A going from 8 to 11. Now, I should tell you that these things are inclusive, all right? So 16 is inclusive as the endpoint. A is inclusive on the other side with the sum 43. Now you'll notice that the A part, we're not concerned about the 0, right? Because we're trading at the end of the day. So now we want to be able to buy the stock before day 8. And then that's to say after day 7, which was up here. After this day, you want to buy the stock at closing and then watch it soar upward and then do its little back and forth until we get here and then sell at 11 before it can plummet again. Okay, so now our divide and conquer solution took us to where we had these 3 different scenarios. All right. And so we know that the maximum subarray is right here. And we know that we're breaking things down to look for where that subarray is. But we also have to be mindful of the fact that the contiguous subarray will lie in certain regions that we cannot necessarily ignore the differences of. All right. So now, here we have the case in which we're crossing the midpoint. And here we have I going to mid. and then mid plus 1 going to j. That's our maximum subarray in reality. So now, possible locations of subarrays of A, low to high, entirely in A would have been all the way over here in this gray part, right? And then entirely in the second half would be over here. And then crossing the midpoint, all right? This guy hypothetically crosses the midpoint, but when we look at our actual data points, we find that that's exactly what we're doing. So that's what the illustration is telling you, all right? But now the question is, how do we work with that crossing? So in B, they say any subarray of low to high crossing the midpoint comprises two subarrays because we have to go from I, which is the lower bound of the maximum subarray, to mid, and then mid plus 1, which continues in the maximum subarray over to j. And so now we see that I is between low and mid, and j is also between mid and high. Okay, so now here's what we do. You're going to take a subarray with the largest sum of the three possible values or the three possible situations. Okay, so that's what we need to do to find a maximum subarray that crosses the midpoint. All right, so now let's backtrack. We'll look at the maximum subarray. The maximum subarray is going to be the one with the I and j. And we know that the low and the highs are just boundaries that are arbitrary. So in our case, it's 0 to 16 or 1 to 16 since it's at the end of the day. But if it were anything else, then we'd have to go with just low and high. And then given that the greatest sum over all the subarrays may lie in some region, either before, after, or through the midpoint, we then need to look at the different subarrays with our divide and conquer strategy. Okay, so now here's what we want to do. We find the maximum subarray crossing the midpoint in time linear in the size of the subarray, which makes sense, right? At worst, we only scan everything. So this problem is not a smaller instance of our original problem because it has the added restriction that the subarray it chooses must cross the midpoint. Now, what we saw in 4.4b, that's actually our current situation. So any subarray crossing that midpoint is itself made of two subarrays because we have to go from I to mid and then mid plus 1 to j. So now in that particular case, we have to find the maximum subarrays of the form of I to mid and mid plus 1 to j, and then try to combine them together. That's going to be our last step. All right. So now for that procedure, we're going to use this find max crossing subarray, and it takes as input the array A, indices low, mid, and high, and then it returns a tuple. Remember that a tuple is an exact set of items in which their order matters, right? So it's an exact um, it's an exact set of items in which we do not like alter either the positions or the number of items in there. If we have a pair, that's a two tuple. If we have a triple, that's a three tuple. But they are what they are, and they're not interchangeable with some other similar description. So now those three are going to contain the indices that are demarcating maximum subarray that crosses the midpoint. In other words, those three different points that make up that max subarray, given the fact that it crossed the midpoint, and now we have to take into account mid and j, right? I, mid, and j. So now, the first thing we want to do is we want to get the left sum. We're claiming that the left sum is currently undefined and that the full sum right now is 0. And now we're going to loop from the mid down to the low. Okay, so we take our sum and we're going to start accumulating values in our sum going from the midpoint down to the low point backwards, okay? So counting going backwards, we're counting the numbers up. We're going to look for a maximum subarray in each part. Now, in this particular case, if the sum is greater than the left sum is equal to sum, which is true, right? We started off with 0. This thing here is undefined, but let's suppose that this was actual programming. You would have a default value of 0. Of course, it's only after we start to accumulate that we can really compare the two, right? Mathematically, negative infinity would always be higher than 0. So now here's what we do. As this thing starts to accumulate, we do the following. We say, okay, so now our sum is greater than the left sum. Left sum is now equal to the sum, and then the max left, right? That's going to be equal to our I. And the max left, remember that before we started with that particular index going from mid to low, okay? So after we've accumulated whatever value that was, right, we're going to update with max left being I. So let's take a look going backwards. Whatever this next thing is, as long as it's higher, if we're getting higher, we're looking at the maximum number, and we're going to give that to our I value, right? So our max left is going to be set equal to I so that we can have something that looks like this in the end. All right. And we're just going to keep backtracking and then making sure that we finally get the boundaries on where we want to be. So now the left sum is equal to the actual sum. Okay. That was something that accumulated upward if the sum is greater than that thing there. Now, let's suppose that we had a situation that did not work that way, right? So let's suppose that we have maybe sum is 33 and left sum is 23, right? So in that particular case, sum is 33, left sum is 23. We say that left sum now becomes 23. And then wherever we found that index where sum was greater, that's going to be our I. All right. So the sum was greater. Instead, we said, okay, now switch the left sum with the sum so that now they're the same. Otherwise, the left sum, if it's smaller, we don't do anything with it. Instead, we come down here and we just say, well, the right sum is equal to negative infinity and sum is equal to 0. And then just like we did up here, we're moving from mid plus 1 to high. Now, this is going to go in the opposite direction, okay, as you can see. So if sum is greater than right sum, here you have sum is equal to sum plus a of j, right, that jth index. And if the sum becomes greater, here you have negative infinity, here we have 0, right? So 0 is greater than negative infinity, so right sum is 0, okay? At this point, they're both 0, but we update the max right to whatever j was. Should it accumulate again, right? What happens then is that as it gets larger, we push this thing out further. So think of it this way. This guy's getting larger. We're moving from mid to high or from left to right. This guy's moving from right to left. So now every time our current value gets larger, we push our subarray out to the right by another index because the accumulation is becoming greater. Now, in the event that the sum is not greater than the right sum, then we just don't do anything there, come back up, and we say sum equals sum plus a, a plus a of j, but this is after we've, incremented, and we look at the next index. If that index causes it to accumulate upward again, and we're going beyond the maximum of what we previously had. Here we had our sum. Here we had the max right as that j, right? So the j is, if the j causes the sum to become larger, and then the sum is greater than the right sum, which was our previous sum, then we push the array out further to the right. So that's growing the subarray out to the right. And then here's what we do. We return from here the max left, which was what we were looking for when we were going in the opposite direction, right? Um, as our left sum was less than sum, in that particular case, we moved our left sum back, right? In this case, if our right sum was less than sum, we moved our right sum forward, right? And as the accumulations take place, we actually pull out the boundaries of our array, but it's only under the following condition. It's only under the following condition that as we look at the sum, right, they're accumulating higher. Let's suppose that sum equals sum plus AI, right? And then now somehow the left sum was the same as the previous sum, but we find that because of this being negative, right, this part here is incorrect, right? This is false. We skip this part, we increment the I to look again, and we keep looking and looking, but we're updating the maximum index for each time it got larger, okay? And we're moving backwards and backwards and backwards. Likewise here, we're keeping track of when the sum gets larger, we're moving to the right. And then after we're done doing that, we then send our different items out. We say, okay, here's the max left, here's the max right, and now here's the left sum plus the right sum. Left sum plus right sum would give us the following. Take a look. If it were from here, we would get 18, right? And then we would stop there. That would be the most that we get. And on this right-hand side, though, we would get 9 minus 7. That gives us 13, but then a 33. Okay? Now, given that we have a 33 there, we find that we never again go any higher, right? If we take away 5 from 33, we get 28. Taking away another 22 from 28, you get 6. Add a 15, that only gives you 21, right? So far, our sums have not improved. Our cumulative sums have not improved since we were at 11. All right, 21. From 21, you get 17 and then 24. That's not the same as what we had over here, where we had 33. Now over here, where we have 18, when you take away from here, that would give you a -5, and then a -21, and -24. Even adding 20 will only get you up to +4. Subtracting would get you back down to -21, -24, and then -11. So now we find that the largest subarray was just this one index, 18, on the left-hand side. And so once we combine those two concepts, after searching through both sides, then we're able to see what the maximum subarray was as follows. Max left was that one index, the ith index, which was 8. Max right, however, was the end of the subarray. Now, the actual sum of the both of them was the values that accumulated between the left and the right parts. And this is our maximum subarray. All right. Now, as for finding the maximum subarray as a whole, here you have With a linear time find max crossing subarray procedure in hand, we can write pseudocode for a divide and conquer algorithm to solve the maximum subarray problem in full. Okay, so here we're going to take the entire array low to high. Okay, I'm going to pause for a second. Just make sure you're all still with me. So, who's still with me 100%? Okay. Oh, one person, two people, four people. Okay, so who is not with me 100%? It's okay to say that. It's okay. Just need to know. Okay, and I guess they don't have that so-so hand that you guys like to do in the actual classroom, so I can't really figure that part out. Let's hear a question or two. Anybody?
Hello. Um,
Yes.
I wanted to say I wasn't here with you like 100%. I just couldn't find the hand thing.
Wait, so you are or you are not?
I am not.
Okay. Question, let's hear it.
I just don't like. I was like gone for a little bit. It was why.
Okay, so what do you understand about the maximum subarray problem?
Um, Not much. I don't know.
Okay,
It's just uh
what was the last thing you understood well? We'll just start from there.
last thing.
Hmm.
Uh, Divide and conquering, and then how that applied to the problem with the maximum subarrays, and then I guess like what was the problem exactly with the maximum subarray?
Okay, so the maximum subarray. Here's what we want to do. So the original synopsis is that um, we're trying to invest in a particular security, particularly a stock, right? And we don't know whether its price is going to be higher or lower over the course of some time. Now we can trade at the end of the day, but not at the beginning. So that's why we went from one to the end of the array. So here's the thing. We don't know when the stock price will be at its lowest or its highest. Now, we're allowed to do this in retrospect. If it's prospectively, we would not know. We can't see the future. But what we're looking to do is to go back into a particular time frame and then really find at what points did the stock price actually accumulate the most from one extreme to the other. So now the reason why that's important is because we want to know what's the greatest possible profit. Rather than just check things from day to day, the better way for us to do things is to look at the change from day to day and then accumulate the change and find out what's the maximum change in value for any component of the subarray. So now, in order to do the divide and conquer part, we cut the array in half. But we can't just get away with jumping in half and then trying to throw things out like what we did with the binary search. Instead, what we need to do is to start looking at both halves of the subarray and then accumulating values to see where those intervals were. Okay. Now, one thing to keep in mind is this: there's no skipping over days because you're buying and holding. So you can't just like mix and match different pieces. It's going to be a continuous time period. So now what we're doing is we're accumulating on both sides of our subarray exactly what the maximum values were and where the greatest accumulation had occurred in any time period in that array. I mean, it could have been the whole array, or it could be something smaller. So that's why we're calling it the subarray that had the maximum value change. That's the maximum subarray. Is that part clear?
Yes, I'm pretty sure we did this yesterday.
Yeah, but we're finishing today.
All right.
Right. So now here's the thing. We said that there's three possibilities. It's possible that if even if we broke the array in half, right? It's possible that what we were looking for, that change, occurred in the first half or interval of the time period, or it could have occurred in the second half, or it could have actually gone over that boundary. So it's kind of like, the opposite of what we did with the binary search, where we threw a half away because we made some assumption that we knew to be correct. In this case, you don't do that, right? So you start at the middle and you work backwards, and you try to find out where that particular index is, right? The indices of both. The only way to actually know that is to be able to work in either direction and start seeing what accumulates and where does the accumulation stop. So to do that, you keep track of two maximum values. The first maximum value tells you that that is, the more positive part of the subarray. Because it is a maximum value compared to the previous day, that suggests a high jump, because when we're comparing the values compared to the previous day into the current day, right? So the maximum value tells us that there was a high jump from the previous day to the current day, and that everything from before means that, there was not such a high jump, or that the change didn't make such a dramatic difference. Now, on the right-hand side of that subarray, we're then looking for another maximum value to tell us where we're ending, right? Because we're basically going from the end of the day to the end of the day. So the first time we see a max, that first end of the day was the highest jump from some lower point. The second time we see a max, that's going to be the highest peak in that entire interval on the right-hand side of the subarray. So in that case, you have the part where the actual values accumulate. So the beginning part with that highest jump, that tells you that that was the interval where there was a big jump from a valley to a peak, right? And then the second part tells you that that's where the peak ends. Like it was still peaking relatively up and down until it got to some maximum high value and then it stopped. And those are the two of those are our cutoffs. Is that
I
clear?
Yes. I What if the maximum peak is on the left hand of the subarray? Like they're both on just one side.
So that would be the first. So that would be the first case in which the whole thing's on the left hand side, right? So what we were doing was the one where it crosses over. So now here's the thing: with the divide and conquer, we have to check for all three. We checked for the third case, which would be the most peculiar and difficult. Right now, we're going to do the simpler part, which is what you're asking. Everybody with me? 100%. All right. Evan says yes. Han says yes. All right. And George says yes. Great. Jared, Jahid says yes. All right. So now here we go. I'm going to go back into the explanation. We're gonna do the full algorithm this time. All right. So we've taken the array, the low and the high. And so here's the full array, not a subarray. And we're going to take in the first index and the highest index. Now, if the array is empty, right, because that's basically what it is. Well, no, that's not true. It could either be empty or it could be only one element. All right. So now we're taking in low, high, And then we're looking at the following. We're going to say return that low was where it began, high is, the part that ended, and A low was the value. There was only one element, so there's nothing to add up there. Otherwise, we say that the mid equals the floor of low plus high over 2. That gets us to the middle of the array. Then we're going to say that we're going to go from left low, left high, and left sum, and find maximum subarray by splitting the first array into the first half. Okay. And then we're going to say, okay, let's also do the same thing for the right part. And the reason why it looks so funny there is if you remember, when we returned 3 values. Okay, so imagine that if this is like Python and you're able to return more than one value and everything is assigned piecewise. Okay. Unlike Java or C where you would have to have an array come back. But anywho, so now here's what happens. You have the right-hand side looking to find the maximum subarray. And then here with cross low, cross high, and cross sum, this was the third part that we did. Okay, so now you're finding the max crossing subarray. We've done that just now. That was the big part. So now if the left sum is greater than or equal to the right sum, and the left sum is greater than or equal to the cross sum, okay, the left sum clearly seems to be the highest of them all. Even if they're all equal, there's nothing wrong with saying that the left sum was correct, all right? However, if the right sum is greater than or equal to the left sum, and the right sum is greater than or equal to the cross sum, then we can also say that the right sum would be the correct answer, and so we can return that. Otherwise, we're going to say that there was a crossed subarray like the one that we found earlier. Okay, so now this was the crossing subarray, and the linear subarray. Did they even care to do that? Nah, it was too trivial, right? All you have to do was find where the two highs occur. But here's how it does work if you're wondering, like, what if it wasn't crossing over? Basically, it would be the following. You would go from the left-hand side. Let's suppose that it was the left-hand side only. Then you would do just this right here. If it was the right-hand side only, then basically it would be just this part right up here, where it ends with the J, right? That's for not crossing boundaries. Okay, and then if it does cross boundaries, you do this big thing. So that's the entire problem, okay? And now you want to analyze the divide and conquer. So here's what we have. So we set up a recurrence that describes the running time of the recursive find maximum subarray procedure, as we did when we analyzed the merge sort into 0.3.2. We make the simplifying assumption that the original problem size is a power of 2, so that all subproblem sizes are integers. We denote by T of n the running time of find maximum subarray on a subarray of n elements. For starters, line 1 takes constant time, and then the base case where n equals 1 is easy. Now, on line 2, we have constant time and so forth, right? So this whole thing, they're saying occurred in roughly constant time. Now, what does that really mean? So for some value n, right, it doesn't matter how large the array is, there's no proportionality or no direct proportionality between the inputs and the size of the subarrays. So I can't say that if only the array were larger, that, it would still be proportional in that area. I wouldn't say that, it's going to be n over 2 somehow. And so technically it's still n. That's not it, right? We can have a subarray of size 5, size 3. If we grew the array out even more so, and it continued on the same way, we would find that no matter how large or small our subarray is, it tops out at linear time. But if it's smaller, we find that one, the answer that we get is just not some proportion of the original, linear number of inputs. So when we see that the left plus the, when we see that the high minus the low plus 1 equals n, and that n is the entirety, and we know we didn't do the entirety, or that the answer could have varied, and there's no way to say that it actually keeps pace with n, then technically it's constant time. Don't be fooled by the 1. It doesn't mean that it's done in 1 step. Even if it were 2 steps or 5 steps, that's still going to be constant time, in which it is t of 1, theta of 1. Okay, so now coming further down, we have the following. The recursive case occurs when n is greater than 1. So lines 1 and 3 take constant time. And by that, they're referring to these up here. Okay. Now, looking further, they're saying the following. Each of the subproblems solved in lines 4 and 5 is on a subarray of n over 2 elements. All right. Now, further, we've got to see the following. Our assumption is that the original problem size is the power of 2, ensures that n over 2 is an integer. That doesn't always mean that it's true, but we're just doing that to make things easier, okay? And so we spent n over 2 time solving each of them. Because we have to solve 2 subproblems for the left subarray, for the right subarray, the contribution to the running time from 4 and 5 comes to 2 times t of n over 2. All right, 2 times a subproblem of half of the whole problem, as we've already seen. So now, this is the, that was in the find max crossing subarray that we did before. All right, and that took theta of n time. So lines 7 to 11 take only constant time, 7 to 11. We're just, comparing and returning. Those take constant time. 1 and 3 took constant time. The only thing that takes linear time is finding the subarrays. So now, the recurrence that they have as an equation would look as follows. T of n equals theta of 1 plus t or 2t of n over 2 plus theta of n plus theta of 1. So now, when simplified, you can drop the smaller terms, okay? So now, the larger terms that remain are 2 times t of n over 2 plus theta of n. And you look at it for what it is, it looks like it's almost linear all the way through, right? But notice what we say here. So now, if n equals 1, only one element, then it's going to be constant. However, if it's not just one element, then what we're going to have is a combination of 2 times t of n over 2, however much work was done recursively, plus theta of n, finding that subarray, okay? So now this is the linear scanning that we did from left to right. And this part was the buildup of those subarrays after we broke things into 2 and we started scanning to see where the endpoints were. Okay, so this recurrence is the same as the recurrence 4.1 for the merge sort, as we shall see from the master method in section 4.5. And that brings us back to where we were. We were talking about the master theorem. Don't want to go too far. So the last time we spoke about the master theorem yesterday, we had one example that fell through the cracks. Okay. It had to do with the regularity of the problem. It looked like it was going to have, a certain recurrence like this here, what you had the merge sort and the maximum subarray. But instead, we found that the regularity problem did not hold, right? So instead, we couldn't use the master theorem to work on that. Now, that left us with discussing the fact that we're going to have to do something else to find the actual analysis of that algorithm if it does not work in the master theorem's general framework. So now here's what we're going to do. Let's go back and we're going to take a look at the actual recursion tree and how it breaks down. So recall that when we have recursion trees, this is 4.4, all right? The substitution method is a bit different. For solving recurrences, guess the form, use mathematical induction to find constants, and show that the solution works, right? What we're going to do instead is look at the tree breakdown. That way you can actually, instead of guessing, really analyze how the work breaks down using the recurrence tree. So the recurrence tree method is in 4.4, as opposed to the master tree method, which is in 4.5. All right. How many people are with me and, get the fact that we're doing something slightly different at this point? 100%. Evan is with me. Shahid is with me. George is with me. Shafi, Han. Okay, let's see. Who else? Let me just stop and take a look. All right. Nafiz. Great. Ula is also with me. All right, great. So we're not losing anybody. Mani is all good too. So then here goes. So this is the tree method. And remember that when we break things down with a tree has certain properties to it. First, I'm going to stop the recording and then start a new one. Okay, so 1 second.